Hello and welcome, ladies and gentlemen, to my step 4 presentation. I'm Alireza Alizadeh and this is CS Internship. In this step, we dealt with file systems and how to handle a file system through Python, how to open files and access the data in them, and how to manipulate them. There are two main ways to do this, which are native to Python. One is os.path and the other one is pathlib. Both have their own workings and their own methods. However, what they do is generally the same thing. The goal they're trying to achieve is the same. Pathlib is a bit more modern, it's a bit more modular, it's object oriented. It doesn't use a string based and procedural methods which can lead to some issues, especially if you're using a string based system. Both can create directories for you, both can destroy directories for you. And so pathlib, since it's more modern, has some useful methods like parent and read text and checking if a file exists or not. And it has some quality of life improvements as well, such as automatically adapting to your OS. So some systems use a slash and others use backslash for their separation in paths. After that, we learn about open and how to open a file and how to read and write to it. You can see all the different modes here. I'm not gonna stay on these for very long because it's pretty rudimentary. Just remember that in conjunction with all these modes and methods, you can use the B flag, so for example RB, to read as binary. So this B represents binary. So if you want to open an email, open an image, or open something that is like a movie or not text-based, you can use this binary mode to achieve that. And after that, we have some read and write methods. Some of them are based in the standard library, some of them are part of the pathlib library, like these two. And with these ideas and these methods and these functions that we learned, we were prompted to open an XLSX file, basically an XLS spreadsheet, right? The problem is you were supposed to do it without using any third-party libraries, so you weren't allowed to use pandas, for example. So what you want to do in these situations is basically Google enough to know that these are basically a bunch of XML files that are zipped together, and you can extract them and access the XML files and read them like that. However, you're not going to be doing operations like this because manipulating them would be really hard, and this is just a proof of concept thing that it's possible and not really functional if you want to manipulate data, especially if you have large data sets. After that, we're going to go through exceptions. Errors in programming happen, and sometimes, more often than you would think, they are a sign that your logic works rather than it's not working. So for example, think about this. You're trying to insert something into a database. So a new line in a database. Database. You get an error that, for example, username exists. Usernames must be unique. This is not a bad thing. You just have to accept it and say, okay, if this happens, do some stuff and prompt user for a new username, because we can't use the username they have provided us. And these error handlings and stuff like this is going to be really useful for you, and it's going to be basically the base of your program and how your program behaves in situations that might otherwise lead to panic. This is the general idea and the general construction of handling exceptions. You try some stuff, you accept something. If it happens, you do some stuff. If it doesn't happen, you do some other stuff. And you have a bunch of code that you want to run anyways. Okay, then use finally. finally, the code that is part of the finally statement always runs regardless. And you have different types of exceptions in Python built in, like value errors and arithmetic errors, name errors, type errors, and OS errors. For example, if you're trying to open a file that is in a part of your system that your program doesn't have access to. For example, if it's a system32 file or a file that's in your root in Linux. So basically stuff like that which are based on permission, they fall on OS errors, and you can, by using classes, define your own exceptions. So for example, you have an exception that is not defined by Python and you want your own exception. Maybe you want a more verbose exception, or something that is useful for your program specifically, you can use a class to define that exception and accept that in your code and insert that in your program to make your program more verbose and a little bit nicer for the end user, and a little bit easier sometimes to maintain. If you have too many exceptions that you have defined by yourself, it's going to make it harder, because someone who's going to maintain the code now has to learn all the exceptions that you have defined, while these exceptions are generally known by most programmers, so you don't have to worry about that. After this, we're gonna wrap up the Python subject and we're gonna move to mathematics. The mathematics section of this step was mostly probability and optimization. The probability part was basically a summary of basic rules in probability, such as the sum rule, and the product rule, and the Bayes theorem, and Bayes. I'm not going to talk about these because these are well known and you can find the formulas online. These are great tools that you are always going to use anytime you're working with any kind of probability, in decision networks and stuff like that. But I'm going to talk about distributions. The book talks about Gaussian distribution or normal distribution, which is a bell curve, basically, which means if you have a bunch of data, the lowest of lows should be minimum, and the highest of highs also should be minimum, and the mid-range should contain most of the data. Now, why is this important? Why do we need this kind of distribution? One use case is in video games and a ranking system. For example, if you have a ranking system like this, which is not calibrated, it's putting too many players in high ranks and not many players in low ranks, which is gonna lead to some matchmaking issues for us. So by calibrating our system, we can achieve a bell curve and we can make our system more sensible. So if you look at this is the same system that we have here, but after 4 or 5 weeks. And now it's calibrated and it's following a Gaussian distribution, as you can see. And the idea is you're gonna have to write systems that their goal is to achieve a normal distribution. And it's not just in the realm of technology, video games, and IT. For example, if you're a college professor and you're creating an exam for your students, if your exam results are in and you have too many perfect scores and you don't have much low scores and your mid scores are not much better either, and most people are getting the maximum score possible, that exam wasn't a standard because a lot of people are getting the perfect score, and that wasn't a good test to determine who's learned and what level of learning they have achieved in their own time. So this is what you're gonna keep in mind sometimes when we talk about mathematics, and especially when reading this book. The book is strictly mathematical and it fails to provide answers and it fails to provide examples that are more graspable for the reader. So for example, if you go to the book and read the sum and product rules and read the distributions, they're all formulas, and there is no like pictures, there is no examples for you. There are examples. I mean, saying there are no examples is a bit unfair, but the examples are in linear algebra, for example, in those kind of environments, and it sometimes becomes a bit conceptual, and it sometimes becomes a bit abstract for the reader and hard to grasp because you really don't know what is happening, and there's a bunch of numbers in front of you. When you understand the relation between the numbers, so you know the relation, but you fail to understand its connection to the real world. What I was trying to do with this example was to show you a connection that is, for example, is something that is in terms of distribution, and it's usually in the realms of exploring data. For example, you have a data set of all the crimes and the fees of each crime, like for example in driving, so for high speed or something like that. And more, it's usually for exploration to see what kind of distribution you have. Sometimes you have to write systems like matchmaking systems like this one to achieve those distributions, which this one doesn't achieve, for example. And the other system that I showed you, which is the same system but more calibrated, it achieves that idea and it achieves that distribution. So it's sometimes for exploration, sometimes to explore, and sometimes it's the goal of your program to achieve that distribution. Moving on, we're going to talk about the last subject matter of this step, and that's optimization. Optimization is basically grabbing what we have and making it better. Making it better. There are a lot of methods to optimize a program, and there are a lot of ways and philosophies on how to optimize. For example, some optimization methods are gonna find you the best solution. So the best solution. But sometimes finding this best solution is costly, and it's costly to a degree that it doesn't even matter to us. So sometimes optimization methods look for a good enough answer. So is it good enough or not? So it's not always for the best, sometimes it's for the best possible with the least cost. Because you have to remember that computers use electricity, use resources, and we can't just give them infinite resources because it's gonna cost us money, it's gonna cost us time, and in a lot of real-time applications, the response time is a lot more important than finding the best solution and the best response to the user in like a more longer time, and then your user has a lot of more waiting time, and it's not going to be a good experience for them, that your program is going to hang, it's not going to be fun. So the idea was we're going to make some stuff better, and sometimes for the best, sometimes for an best case, sometimes for something that is good enough. Book talks about a lot of methods. I'm just going to talk about one, and that's gradient descent, which is this picture right here. The idea of gradient descent, when you look at it mathematically, is a bit hard to grasp. So bear with me here. We're going to go through an example in real life. So think about this. You are at top of a mountain. This outer circle here is the top of a mountain. And this inner circle is basically where you started from, and it's the bottom of the mountain. You are climbing a mountain and you are stuck in a thick fog. a fog to a degree which you can't see your next step. So you're stuck in a fog. You can't see. Can't see. And you want to go down and reach the bottom of the mountain and go home before the sunset. Now, what do? The fog is so thick that you can't see your next step. So you don't know which way is down or which way is up. But you have a measuring tool which measures the steepness of your step in some direction that you choose to go. So you have a measuring tool as well. You measure a couple of directions and choose the steepest one, right? Because you want to go down, and the fastest way to go down is to choose the steepest direction. So which way is the steepest? And you take your step. How long do you take these steps in that direction? We don't know. You can, in principle and in theory, use your tool every step. So every step you can use your tool. But the problem with this is it's going to take a lot of time, and you're going to be stuck in the mountain in the night, and the wolves are going to eat you. So when do you use your tool? How many steps do you take after each measurement? These are all parameters that you want to consider when using gradient descent. Because yes, it's going to find you the bottom of the mountain and you're going to go home, but how fast and how costly that's going to be is based on your parameters that you set for yourself. How many steps am I taking? How many times am I measuring with my tool to find out the steepest way? So you might sometimes, don't not go down in a very direct way. So you might measure and go this way and keep continuing this way, and then measure and correct your path. It's not an always improving algorithm. It sometimes might go in the wrong direction if you use the wrong step number or you don't use your measurements properly. So for example, think about this. I have had my measurements, and this way was the steepest one that I could go. And I just continue this way without measuring. I'm just completely missing our goal, which is here. So this is the idea of gradient descent. I hope I was able to give you a basic idea of how it works. It's basically climbing a mountain or descending from a mountain, whichever what you want to call it. Climbing is going to be maximizing, and descending is going to be minimizing. So for example, if you have an error function that you want to minimize with gradient descent, you're going to basically think about this. I'm in a mountain. I want to find the bottom. How many times do I measure? How many steps do I take in that direction? And all that. And that's all, folks. Thanks for listening, and I hope you enjoyed. Bye-bye.
خسته نباشی.
سلامت باشی.